Geophysical MASINT is a branch of measurement and signature intelligence that involves phenomena transmitted through the Earth and man-made structures including emitted or reflected sounds, pressure waves, vibrations, a magnetic field or ionosphere disturbances. According to the United States Department of Defense, MASINT is technically derived intelligence that, when collected, processed, and analyzed by dedicated MASINT systems, results in intelligence that detects, tracks, identifies, or describes the signatures of fixed or dynamic target sources. MASINT was recognized as a formal intelligence discipline in 1986. Another way to describe MASINT is a non-literal discipline. It feeds on a target's unintended emissive byproducts, the trails, the spectral, chemical or RF that an object leaves behind. These trails form distinct signatures, which can be exploited as reliable discriminators to characterize specific events or disclose hidden targets. As with many branches of MASINT, specific techniques may overlap with the 6 major conceptual disciplines of MASINT defined by the Center for MASINT Studies and Research, which divides MASINT into electro-optical, nuclear, geophysical, radar, materials, and radio frequency disciplines. Military requirements. Geophysical senses have a long history in conventional military and commercial applications, from weather prediction for sailing, to fish finding for commercial fisheries, to nuclear test ban verification. New challenges, however, keep emerging. For First World military forces opposing other conventional militaries, there is an assumption that if a target can be located, it can be destroyed. As a result, concealment and deception have taken on new criticality. Stealth, low observability aircraft have gotten much attention, and new surface ship designs feature observability reduction. Operating in the confusing literal environment produces a great deal of concealing interference. Of course, submariners feel they invented low observability, and others are simply learning from them. They know that going deep or at least ultra-quiet, and hiding among natural features, makes them very hard to detect. 2 families of military applications, among many, represent new challenges against which geophysical MASINT can be tried. Also, see unattended ground senses. Deeply buried structures. One of the easiest ways for nations to protect weapons of mass destruction, command posts, and other critical structures is to bury them deeply, perhaps enlarging natural caves or disused mines. Deep burial is not only a means of protection against physical attack, as even without the use of nuclear weapons, there are deeply penetrating precision-guided bombs that can attack them. Deep burial, with appropriate concealment during construction, is a way to avoid the opponents knowing the buried facility's position well enough to direct precision-guided weapons against it. Finding deeply buried structures, therefore, is a critical military requirement. The usual first step in finding a deep structure is IMINT, especially using hyperspectral IMINT senses to help eliminate concealment. Hyperspectral images can help reveal information not obtainable through other forms of imagery intelligence such as the moisture content of soil. This data can also help distinguish camouflage netting from natural foliage. Still, a facility dug under a busy city would be extremely hard to find during construction. When the opponent knows that it is suspected that a deeply buried facility exists, there can be a variety of decoys and lures, such as buried heat sources to confuse infrared sensors, or simply digging holes and covering them with nothing inside. MASINT using acoustic, seismic, and magnetic senses would appear to have promise, but these senses must be fairly close to the target. Magnetic anomaly detection is used in anti-submarine warfare for final localization before attack. The existence of the submarine is usually established through passive listening and refined with directional passive senses and active sonar. Once these senses have failed, there is promise for surveying large areas in deeply concealed facilities using gravimetric sensors. Gravity sensors are a new field, but military requirements are making it important, while the technology to do it is becoming possible. Naval operations in shallow water, especially in today's green water and brown water naval applications. Navies are looking at MASINT solutions to meet new challenges of operating in littoral areas of operations. This symposium found it useful to look at 5 technology areas, which are interesting to contrast to the generally accepted categories of MASINT: acoustics and geology and geodesy, sediments, transport, non-acoustical detection, physical oceanography, coastal meteorology, and electromagnetic detection. Although it is unlikely there will ever be another World War II-style opposed landing on a fortified beach, another aspect of the littoral is being able to react to opportunities for amphibious warfare. Detecting shallow water and beach mines remains a challenge, since mine warfare is a deadly, poor man's weapon, while initial landings from an offshore force would be from helicopters or tilt-rotor aircraft, with air cushion vehicles bringing ashore larger equipment. Traditional landing craft, portable causeways, or other equipment will eventually be needed to bring heavy equipment across a beach. Shallow depth and natural underwater obstacles can block beach access to these craft and equipment, as can shallow water mines. Synthetic aperture radar, airborne laser detection and ranging, and use of bioluminescence to detect weight trails around underwater obstacles all may help solve this challenge. Moving onto and across the beach has its own challenges. Remotely operated vehicles may be able to map landing routes, and they, as well as LiDAR and multispectral imaging, may be able to detect shallow water. Once on the beach, the soil has to support heavy equipment. Techniques here include estimating soil type from multispectral imaging, or from an air-dropped penetrometer that actually measures the load-bearing capacity of the surface. Weather and sea intelligence MASINT. The science and art of weather prediction used the ideas of measurement and signatures to predict phenomena, long before there were any electronic sensors. Masters of sailing ships might have no more sophisticated instrument than a wetted finger raised to the wind, and the flapping of sails. Weather information, in the normal course of military operations, has a major effect on tactics. High winds and low pressures can change artillery trajectories. High and low temperatures cause both people and equipment to require special protection. Aspects of weather, however, also can be measured and compared with signatures, to confirm or reject the findings of other senses. The state of the art is to fuse meteorological, oceanographic, and acoustic data in a variety of display modes. Temperature, salinity and sound speed can be displayed horizontally, vertically, or in three-dimensional perspective, predicting weather based on measurements and signatures. While early sailors had no senses beyond their 5 senses, the modern meteorologist has a wide range of geophysical and electro-optical measuring devices, operating on platforms from the bottom of the sea to deep space. Prediction based on these measurements are based on signatures of past weather events, a deep understanding of theory, and computational models. Weather predictions can give significant negative intelligence when the signature of some combat system is such that it can operate only under certain weather conditions. Weather has long been an extremely critical part of modern military operations, as when the decision to land at Normandy on June 6, rather than June 5, 1944 depended on Dwight D. Eisenhower's trust in his staff weather advisor, Group Captain James Martin Stagg. It is rarely understood that something as fast as a ballistic missile re-entry vehicle, or as smart as a precision-guided munition, can still be affected by winds in the target area. As part of unattended ground senses, The Remote Miniature Weather Station, from System Innovations, is an airdroppable version with a lightweight, expendable and modular system with two components: a meteorological sensor and a ceilometer with limited MET. The basic MET system is surface-based and measures wind speed and direction, horizontal visibility, surface atmospheric pressure, air temperature and relative humidity. The ceilometer sensor determines cloud height and discrete cloud layers. The system provides near real-time data capable of 24-hour operation for 60 days. The RMWS can also go in with U.S. Air Force Special Operations Combat Weatherman. The man-portable version, brought in by combat weathermen, has an additional function, as remote miniature ceilometer, designed to measure multiple-layer cloud ceiling heights and then send that data via satellite communications link to an operator display. The system uses a neodymium YAG, 4 MW non-eye-safe laser. According to one weatherman, "We have to watch that one," he said, "leaving it out there. Basically we're worried about civilian populace going out there and playing with it, firing the laser, and there goes somebody's eye." There are two different units to RMWS. One has the laser and one doesn't. The basic difference is the one with the laser is going to give you cloud height. Hydrographic Senses Hydrographic MASINT is subtly different from weather, in that it considers factors such as water temperature and salinity, biologic activities, and other factors that have a major effect on senses and weapons used in shallow water. ASW equipment, especially acoustic performance, depends on the season, the specific coastal site. Water column conditions, such as temperature, salinity, and turbidity, are more variable in shallow than deep water. Water depth will influence bottom bounce conditions, as will the material of the bottom. Seasonal water column conditions are inherently more variable in shallow water than in deep water. While much attention is given to shallow waters of the littoral, other areas have unique hydrographic characteristics. Regional areas with freshwater eddies, open ocean salinity fronts, near ice flows, under ice, a submarine tactical development activity observed. Freshwater eddies exist in many areas of the world, as we have experienced recently in the Gulf of Mexico using the Tactical Oceanographic Monitoring System. There exist very distinct surface ducts that causes the Submarine Fleet Mission Program Library sonar prediction to be unreliable. Accurate bathythermic information is paramount and a precursor for accurate sonar predictions. Temperature and salinity critical to the prediction of sound, needed by active and passive MASINT systems operating in water, is knowing the temperature and salinity at specific depths. Anti-submarine aircraft, ships, and submarines can release independent sensors that measure the water temperature at various depths. The water temperature is critically important in acoustic detections, as changes in water temperature at thermoclines can act as a barrier, or layer, to acoustic propagation. To hunt a submarine, which is aware of water temperature, the hunter must drop acoustic senses below the thermocline. Water conductivity is used as a surrogate marker for salinity. The current and most recently developed software, however, does not give information on suspended material in the water or bottom characteristics, both considered critical in shallow water operations. The U.S. Navy does this by dropping expendable probes, which transmit to a recorder, of 1978 to 1980 vintage. The IMINT-BQH-7 for submarines and the IMINT-BQH-71 for surface ships. While the redesign of the late 70s did introduce digital logic, the devices kept hard to maintain analog recorders, and maintainability became critical by 1995. A project was begun to extend with COTS components, to result in the IMINT-BQH-7 AEC3. In 1994-5, the maintainability of the in-service units became critical. Variables in selecting the appropriate probe include maximum depth sounded, speed of launching vessel, resolution, vertical distance between data points, Depth accuracy. Biomass. Large schools of fish contain enough untrapped air to conceal the seafloor, or man-made underwater vehicles and structures. Fish finders, developed for commercial and recreational fishing, are specialized sonars that can identify acoustic reflections between the surface and the bottom. Variations on commercial equipment are apt to be needed, especially in littoral areas rich in marine life. Sea bottom measurement. A variety of sensors can be used to characterize the sea bottom into, for example, mud, sand, and gravel. Active acoustic senses are the most obvious, but there is potential information from gravimetric sensors, electro-optical and radar sensors for making inferences from the water surface, etc. Relatively simple sonars such as echo sounders can be promoted to seafloor classification systems via add-on modules, converting echo parameters into sediment type. Different algorithms exist, but they are all based on changes in the energy or shape of the reflected sound pings. Side-scan sonars can be used to derive maps of the topography of an area by moving the sonar across it just above the bottom. Multi-beam hull-mounted sonars are not as precise as a sensor near the bottom, but both can give reasonable three-dimensional visualization. Another approach comes from greater signal processing of existing military sensors. The U.S. Naval Research Laboratory demonstrated both seafloor characterization, as well as subsurface characteristics of the seafloor. Sensors used in different demonstrations included normal incidence beams from the UQN-4 surface ship depth finder, and BQN-17 submarine fathometer, backscatter from the Kongsberg M121 commercial multibeam sonar, and UQN-4 fathometers on mine countermeasures ships, and the AQS-20 mine hunting system. These produce the bottom and subsurface characterization graphic. Weather effects on chemical, biological, and radiological weapon propagation. One of the improvements in the Fuchs 2 reconnaissance vehicle is adding onboard weather instrumentations, including data such as wind direction and speed, air and ground temperature, barometric pressure and humidity.